All right, so let's do a couple of example problems. So at the end of your lesson, you should have two problems, and we're going to go through and do these together. Or actually, you're going to do them. I keep telling Veronica, she's probably tired of hearing this, but the older I get, the lazier I get. And so I'll be on standby if you have questions. We'll talk about these problems very quickly, but then you'll solve them, and then we'll compare your answers to our answer. You should have a problem that looks like this, right? Are you seeing this? Your workbook? So let's go through this, talk about it, and then you can do the calculations. All right, so the velocity of the upstream end of a rectangular channel that's 3 feet wide is 10 feet per second, and the flow depth is 6.5 feet. The depth at the downstream end is 5.5 feet. The elevation at section 1 is given 1640.5, and the elevation at 2 is 1640. Determine the head loss due to friction, and assume the kinetic energy correction factor is 1. We're not going to go into that too much. That's pretty common though, okay? So whenever you hear head loss, then that should automatically trigger, well, I need to use the energy equation, right? Yeah. And you have just about everything that you need for the energy equation to solve for the head loss, because you know the energy up here is the same as the energy down here, plus this head loss here. So you can actually do that calculation, and if you have everything, then you calculate that H sub L. You're actually missing one piece of information, and that is the velocity down here, right? So you actually need to calculate the velocity down here. So you have two unknowns, you have to use two equations. So the energy equation is the primary one. What other equation can you use to calculate the velocity down here? Q equals AV, continuity. That's exactly right, and that's all this problem is doing. And it kind of leads you through that process. So why don't you spend 5 or 6 minutes and go through that, and then we'll compare answers. So the first thing you want to do, again, is use continuity and figure out what the velocity is down here. Plug your values in the energy equation. Let's talk real briefly about this first problem. So we said we had just about everything we needed to plug into the energy equation so we could solve for the head loss between points 1 and 2. We did not have the velocity at the downstream section. However, giving our good friend continuity, we can say that Q is equal to V1A1, right? And then we start plugging in our known values, and we come up with our Q of 195 CFS. So at section 2, Q remains constant from points 1 and 2, so we know that's still 195. We do not know the velocity, but we know the flow area because it's a rectangular channel. So we plug in that information, and we solve for the average cross-sectional velocity of 0.2 and come up with about 11.8 feet per second. Pause there because what Veronica mentioned about significant figures is indeed significant. We have perception issues in hydraulics. It has been commonplace, and I think a lot of this has been driven by FEMA, that we tend to report our calculations and our design values in hundreds. 11.01 feet. It's not 11.01 feet, guarantee it. Probably not 11.0 feet. It may not even be 11 feet. However, when we continue to report these significant figures to folks, they may get the wrong idea about how precise and accurate we can be with our calculations. Sometimes, as you've seen from the discussion of the regression equations, the rational method, are we within 20% of the real answer? Well, that's pretty darn good. 30%, 40% is maybe more realistic of what our expectation is. Sometimes it's just a gross guess. And when we have a lot of uncertainty in our answers, that forces us in high-risk situations to be overly conservative, or very conservative. I don't want to say overly conservative. It forces us to be very conservative with our calculations, and then we try to plan for the worst-case conditions, right? So when you're reporting out numbers, if this is a velocity you're giving to someone, we're doing ourselves a disservice. I would probably say that's 11.8 feet best case scenario, but maybe I would even just say it's about 12 feet per second. Use the energy equation then to find the head loss. So we have all of the known information except for head loss now. So we plug in and we get our velocity head at 0.1. Our pressure head at 0.1 is just the depth of water. And we're given the elevation head. That's the datum. That's the datum of the ground surface. And then again, we have all the information at 0.2. And then we solve for head loss, and we see the head loss between points 1 and 2 is about 0.88 feet. Did anyone not get that, or does anyone have questions on that calculation? How do you think that head loss occurred? Through what mechanism? Most likely through friction. We have this one here next, right? Given your trapezoidal earth channel. When you see B, capital B in hydraulics lingo and equations, that's typically the bottom width of your open channel. That said, we tend to use the same variables to talk about different things. It's one of the things that gets us into trouble, and one of the things that irks people that we deal with. But capital B usually is the bottom width, and that's given as 6.5 feet. The side slope, whenever you're talking about side slope, sometimes it's vertical to horizontal, sometimes it's horizontal to vertical. I always like to see this in parentheses at least, so that I know for sure, because it gets very confusing for me. I always forget which one is coming first. The side slope is 1 vertical to 2 horizontal. The equation that we're going to use when you see Z, that's just the horizontal component of that side slope ratio, so it's going to be 2. The slope is 0.003. Normal depth is Y. So when you hear normal depth, what equation do you think we're going to be using? Normal depth. Normal depth only comes from one equation. It starts with an M. Manning's equation. Manning's equation gives you the flow depth that would normally occur in a channel under steady uniform flow conditions until we go in and mess it up by putting in culverts and bridges and other types of things. Okay? So normal depth comes from Manning's equation. And that's given us 1.6 feet. And we're given a roughness value of 0.02. And we want to find the velocity in the discharge. Well, it sounds like we can just use Manning's equation for that. No worries. So Manning's equation, again, is right here. We're looking for velocity. We have our conversion of 1.49 so that it's in US customary units. We're given a roughness value of, I forgot it already, 2.02? Yeah. And now we have this hydraulic radius and our channel slope, because we have steady uniform conditions, so we're just using channel slope. We're given that value. Hydraulic radius is a ratio of flow area to the wetted perimeter, or the boundary that's wetted by that flow. Okay. So the flow area, if you look up in HDS4, Introduction to Highway Hydraulics, it has a fancy equation for the flow area in a trapezoidal section. You could actually do this through geometry if you don't trust these fancy equations that are generated. How would you do that? It's pretty straightforward geometry. Right? So you wanted to calculate the area of the trapezoid. Say the flow is here. I'm actually going to use blue. I feel like being fancy. Try to use purple. Maybe my water's purple. Very easy. All right. So if I want this flow area, which this equation will actually give you by plus zy squared. Well, if I actually wanted to do this on my own, I would just say, well, I have a triangle here, I have a triangle here, and I have a rectangle here. Well, the rectangle's easy. This is 6.5. And the flow depth, I think I was given that as, what is it again? 1.6. 1.6? Yeah, so it's just 1.6 times 6.5, and I have flow area of the rectangle. Now I have to do the two triangles. Well, I know this is 1.6. So if this comes up 1.6, it goes over twice that, right? Because the ratio of the side slope is 1 vertical, 2 horizontal. So if it comes up 1.6, it goes over 3.2. So this is 3.2. And then it's just 1/2 base times height, and I have the area of this triangle, and then I multiply that by 2. And I have the area of the two triangles, and I add that on to the area of the rectangle. Or you could just use this equation, which is the 6.5 times 1.6 plus 2 times 1.6 squared, and you get the same answer. So that's the flow areas. Now another fun one is the wetted perimeter. So I want the length that the water is in contact with, the length of my boundary that the water is in contact with, and that is the wetted perimeter. Well, so that's this piece here, plus this piece here. You could use this equation right here for the wetted perimeter, b plus 2y square root of y plus z squared, where again z is your 2. Or if you wanted to go back to your geometry roots and do it the fun old-fashioned way, you could say, well, this is 6.5. This is the hypotenuse of a right triangle. I know that a squared plus b squared equals c squared, right? So I can calculate what this is and take the square root of it, and then I have this length here, and then I multiply that by 2, and that will give me these two, and then I add on to 6.5. Okay, basic geometry. So again, there's usually more than one way to. There's usually more than one way to.
Skin a cat.
No. There's more than one way to brush a cat. We don't skin cats around here, at least not around me. There's more than one way to brush a cat. So that's just about with anything in hydraulics. There are different routes to get to the same slope. Okay? So you can go ahead and do that. You can calculate your hydraulic radius again, which is area over the wetted perimeter. Plug in all the information here, calculate your velocity, and then we know that the total Q is area times velocity, and we can figure that out. So go ahead and take a minute to review those and crunch your numbers and compare with the solution here. Still writing. A couple of folks are retweeting Donald Trump. Do you have questions on that? So that was an application of which equation? Manny's equation gives you what depth?
Normal depth.
And Manny's equation is used for what flow conditions?
Steady, uniform.
So for your roadside ditch designs, 99 times out of 100, you're most likely using Manning's equations, right? If you know your design flow, which you calculate from your hydrology, and you calculate your flow depths and your velocities and shear stresses, and then we're going to show you in the next lesson what you can do with that that will help you with your ditch design. All right, so let's just go back and revisit our learning outcomes that we're going to take a break.
2 times 1.6 squared. There's area.
Yeah.
How is that the area?
I am going to save the toolbox demo for the next one because we're going to be kind of revisiting some of the similar concepts that we want to hear.
Okay, so it's treated here with just 1 square.
So what are some ways we describe the types of flow moving channels? Yes, uniform, non-uniform, gradually varied flow, and that's a description of flow depth and flow depths and velocities with distance. Okay, what else? Steady and unsteady, and that's a description of how the flow changes with time. Okay. We also talked about subcritical and supercritical flow. So if you were talking with your pet, perhaps it's a cat or a dog, and you were just trying to wind down at the end of the day, and you were talking about subcritical flow, you might say to your BFF, your best furry friend, that subcritical flow is deep, tranquil, slow moving, lots of potential energy, right? And vice versa, supercritical flow, fast moving, lots of kinetic energy, kind of rapid, turbulent. Those are all good ways to describe supercritical flow. The Freud number for subcritical is less than 1, and for supercritical is 1. The flow depth of supercritical flow is what compared to critical depth? Less, right? It's shallow, it's less than critical depth, and subcritical flow is greater than critical depth. Manny's equation can be used in steady uniform flow conditions to get normal depth, average cross-sectional velocities, which can then lead to calculations of shear stress. 3 fundamental equations in hydraulics we talked about. Mass energy, momentum, conservation, correct. And then we actually did a couple of quickie problems. Okay. Any questions?